Hello party people. In this video, I will just be going over the mechanism for acid catalyzed hydrolysis of amides. So let's say you have some H plus source. In acidic conditions, you will have some excess H plus. So this could come from, for example, an H3O plus. So this hydrogen is our target. Target of whom? Well, you must consider resonance structures always. So if I drew a resonance structure, right now I'm forgetting that the H3O exists. Draw in my resonance arrows. I see that the nitrogen has a lone pair. Nitrogens are very good bases. So I can go 2 in, 2 up. So a prominent structure will be where the oxygen, that makes sense because it's an electronegative atom, has the negative charge, and the nitrogen has a positive charge. So who's more likely to attack the H plus? Well, it's going to be the guy or the girl that is more nucleophilic. So who has more electron density? Resonance tells us that the electron density is primarily on that oxygen. You can think about this in 2 steps. So if the nitrogen goes 2 over or 2 in, 2 up, we get a negative charge on that oxygen. So the oxygen is nucleophilic, hence it wants to attack things that are delta plus, so it could attack this hydrogen via 2 in, and then the 2 electrons in the OH bond will go 2 up, and then the oxygen will become neutral again. The O is now protonated, so it's neutral. Everything else stays the same. The nitrogen, though, it's still unhappy. It is charged, so we need to figure out a way to remove that charge on the nitrogen. Hence, the nitrogen needs to gain a lone pair. How could this occur? Well, remember, when the OH3 lost a proton, we got water. And what is water? Water is a great nucleophile. It is very small and it has lone pairs. So this O can then attack the carbon via 2 in, and then the 2 electrons in the CN bond can flick up onto that nitrogen, and the nitrogen will become neutral. Yes, that's what we want. A trick when performing mechanisms is to draw everything the same that did not change. So R1 did not move. The OH group did not move. So draw in all that. The single bond to the nitrogen is still there. The nitrogen is still bonded to R2 and to R3. All that's changed is, well, wherever you draw an arrow, if it's coming from a lone pair, then that will become a new bond. So there's a new bond there. Who did it come from? Well, it came from the oxygen. And that oxygen still has 2 hydrogens attached to it. So now it is positively charged. Lose electrons become cationic. And the nitrogen gained the 2 electrons in that CN bond. So now it is neutral. So now we have to fix another problem. Well, the oxygen here is now charged. No atom wants to be charged. So what happens? I think as a second-year student, we all forget, and I did this too, that these reactions happen in a solution where each reagent is in the flask at a certain concentration. So that means where there was 1 of something, there's always more in that solution. So proton transfers can occur whenever an atom has a charge. So if an atom has a positive charge, proton transfers occur to make that atom neutral. And it usually comes from the solvent. So let's say there's more OH2 in the flask. It could go 2 in, 2 up. So the oxygen on our actual substrate will become neutral. So drawing the product of the proton transfer, all that happens is you copy and paste everything except for you remove 1 of the hydrogens, and the atom that you remove the hydrogen from becomes neutral. So now we have this. But what you also got in the process was an OH3 plus. So now you got to ask, okay, well, who wants to attack one of the hydrogens on the OH3 plus? Well, we know our nitrogen is a really good base. So it can go 2 in, 2 up. Oh, we have another proton transfer. What happens now? Well, the nitrogen will become positively charged. So drawing everything the exact same except the nitrogen now will be attached to the proton that it attacked. Well, that means this nitrogen's now cationic. Yes, that is very true. It's also a really good leaving group, because what does it want? Well, it wants a lone pair. So what happens now? Well, one of these lone pairs on one of the oxygens can go 2 in, and then the 2 electrons in the carbon-nitrogen bond can go up onto the nitrogen. And you regenerate that double bond that was initially present in between the carbon and the oxygen. R1, double bond, and I'm going to draw this in a weird way, so the way that I see it, how it started, and then I will draw things in a proper form after, but I find that this is the best way to approach drawing the final product to get it correct. So just draw it exactly how you see it first, and then you can switch things up later to make it look better for your TA who's going to be marking it. So now this oxygen is positively charged. We still have a bond to the OH, and like I said, we're drawing this exactly how we see it on the left-hand side, just so we don't mess things up. And what we get is a neutral leaving group. But then we say, things aren't right here, right? Because this oxygen is still charged. Every atom with a charge, well, what happens? A proton transfer. So the nitrogen could go and grab this hydrogen 2 in, 2 up onto the oxygen to neutralize that oxygen. So what do we get? Well, draw the exact same thing, but the oxygen has now gained a lone pair, and it is now neutral. So instead of drawing the OH group on the left-hand side, well, I'm going to draw it on the right-hand side, just so it looks nice. OH. And then my other product would be the NH2R2. So 2 R groups, R2 and R3. I'm just saying that there's 2 of them, 2 R groups, where the R groups would be R2 and R3, and this is whatever your teacher shows you. It could be a phenol group. It could be a huge alkyl chain. It literally doesn't matter. The mechanism will stay the same. But just so we don't have any confusion, I will write it like this. R2, R3, and H2. And the nitrogen will be positively charged. And then if you want to say, well, how does this get neutralized in the end? Still have OH2 in the solution. So a water could go and neutralize the nitrogen. And then you would have neutral species in solution, and whatever generated the H3O plus in the beginning will come back. Let's say it was H2SO4, and it will grab that third hydrogen, and you will get neutral water as well. But that is quite irrelevant to this mechanism. All that matters is the many steps that we just went over in this video here. Yeah, I hope this was helpful. Sorry, it was a quick video. I thought this would be helpful, as I know it is one of the concepts that is being going over in class right now. Yeah, I have a lot to do for my own work, but I don't want to leave you guys hanging. So, hope this video was helpful, and hope you have a great night. Please make sure to leave a like, comment, save, and or subscribe to my channel if you like my content. Have a great night. Bye!